This is a series of videos discussing the differential expressions in AP Physics C mechanics. We start with our chapter 1 equation. Velocity is the derivative of s with respect to t, so the derivative of displacement with time. Acceleration, of course, is dv dt, or the second derivative of displacement with respect to time. To get average speed or velocity, we use the mean average theorem from calculus. The derivative of ds from t1 to t, or the integral of ds from t1 to t2 divided by t2 minus t1. Essentially, that's the total displacement over time, or the total distance over time. Depending on if you want velocity, it's displacement. If you're looking at speed, it's distance over time. Now, what about average acceleration? Of course, we'll integrate the acceleration time from t1 to t2 over t2 minus t1, which is essentially the change in velocity with respect to time. Now, what about instantaneous velocity? Well, instantaneous velocity, of course, is a limit of delta s over delta t as delta t approaches 0, or simply ds dt, or the slope of the tangent drawn to the curve of displacement versus time. Instantaneous acceleration, of course, is a limit of delta v over delta t as delta t approaches 0, or simply the derivative of velocity with respect to time, or essentially the slope of the tangent of the velocity versus time graph. Now, what about forces? F equals ma can be written acceleration equals force over mass. What's acceleration? Acceleration, of course, is dv dt, which equals F over m, or it's the second derivative of s with respect to time, which also equals F over m. Now, what about our work energy theorems? Well, we know that dw, the derivative of work, equals force times ds. Therefore, work is the integral of force ds from s equals 0 to s. Work also equals minus delta U, so the change, the negative change in potential energy is what is work. So if we see a decrease in potential energy, that will be an increase in work. And what does that mean? Well, work equals change in kinetic energy. So potential energy is essentially converting into kinetic energy in that equation. That assumes no non-conservative forces. Now, what if there are non-conservative forces like friction? Well, I like to use the idea of work net equals work conservative minus work non-conservative, which of course goes into the change in kinetic energy. Now, what about spring constant? Well, the force of a spring equals minus kx. Remember, the minus tells us that it's a restoring force. If I pull a spring to the right, the force, of course, will be negative, and vice versa. Now, we can substitute ma equals minus kx, but divide both sides by m. Acceleration equals minus kx divided by m. Now, acceleration is the second derivative of x with respect to time, which equals minus kx over m. And we'll use that in our derivation of our simple harmonic motion equations. Now, what is force, Miko? Force is going to equal minus du dx, the derivative of u with respect to x. How can we apply that? Well, let's say we take the force of a spring would be the derivative of the elastic potential energy of a spring. The derivative of 1/2 kx squared equals kx. And of course, if we take the second derivative of that, we can get the k constant. So the derivative of force with respect to x, or the second derivative of potential energy versus x, is equal to k. Now, what about power? Power is going to equal force times ds dt. What does this mean? It's how quickly work can get done. So force times time. So again, power is force times ds dt, or power equals derivative of work with respect to time. It's really how quickly work can get done. And power can also be force times velocity. This last equation comes from ds dt equals velocity. Force times velocity. This one can be used for instantaneous velocity calculation. So in other words, if I know what instantaneous velocity, I can then figure out what power is at that particular velocity. Or if I've got an average velocity, just multiply the force by that average velocity, and I get average power. So however it is you want to use that. Next would be momentum. The force net acting in a system is equal to dp dt, the instantaneous change in momentum with respect to time. Here, p means momentum. Now, j is impulse. If we integrate force times time, or force dt, from t1 to t2, we can then get the total change in momentum for the system. Okay? So force times time equals momentum. Now what about getting average force? Well, using the mean value theorem again, we take the integral of force dt from t1 to t2, and of course divided by t2 minus t1. We'll essentially get the change in momentum with respect to time. And next, we'll have a circular motion. We'll do the beginning part of circular motion here. So omega, angular velocity, equals d theta dt. Alpha, angular acceleration, of course, is dw dt, or alpha is the second derivative of theta with respect to time.